Welcome to the lecture on nonlinear programming. This lecture is for chapter 10 of our course Operations Research. Like linear programming, nonlinear programming is a mathematical technique which minimizes or maximizes the objective function subject to a set of constraints. The basic difference between linear programming and nonlinear programming is that in linear programming, both the objective function and the set of constraints are linear, whereas in nonlinear programming, either the objective function or some constraints or both are nonlinear. In solving linear programming problem, we find the solution at the extreme point of the feasible region, whereas the solution of the nonlinear programming problem can be obtained anywhere at the boundary of the feasible region or even at the interior point, at any interior point of the feasible region. There are several techniques developed for solving nonlinear programming problem, but an efficient method like simplex method has not yet been developed. In this chapter, we will develop or we will discuss several solution techniques for nonlinear programming problem. The content of this chapter will be covered in 3 modules. So, let us start our discussion on module 1 of this chapter. In this module, we will introduce nonlinear programming and discuss nonlinear programming problem with equality constraints and Lagrange multiplier method. Nonlinear programming problem. Let Z be a real valued function of n variables x1, x2 up to xn. Therefore, we define Z equal to f x1, x2, xn. Let b1, b2, bn be a set of constants such that g1, x1, x2, xn is less than equal to or greater than equal to b1. g2, x1, x2, xn is less than equal to or greater than equal to b2, and similarly gm x1 x2 xn is less than equal to or greater than equal to bm, and of course we have xj is greater than equal to 0 for all j equal to 1 to up to n. This is the non-negativity restrictions. Here the functions gj's are real valued function. Now, if either f or some gi's or both are nonlinear, then the problem of determining x1, x2, xn, that is the decision variables which makes z a maximum or minimum and satisfies the constraints is called nonlinear programming problem or NLPP. In matrix notation, the NLPP may be written as follows. Determine x belongs to Rn so as to maximize or minimize the objective function z equal to fx, subject to gix is less than equal to or greater than equal to bi for I equal to 1 to up to m, and x is greater than equal to 0 where x is equal to x1, x2 up to xn belonging to Rn. Here either fx or some gix or both are nonlinear in x. Sometimes it is convenient to write the constraints gix less than equal to or greater than equal to bi as hix less than equal to or greater than equal to 0 where hix is equal to gix minus bi. Now, we proceed to discuss Lagrange multiplier method, which is a very popular method in solving NLPP with equality constraints. If a nonlinear problem is composed of some differentiable objective function and equality constraints, then the optimization may be achieved by this method. Now, we shall develop this method for a function of two variables only. Later, we will generalize the arguments for any number of variables. Suppose that we have to find an optimal value of a differentiable function f x y, whose variables are subject to a constraint g x y equal to 0, where g is also differentiable. If such an optimum occurs at a point x 0 y 0, at which at least one of the partial derivatives del g del x or del g del y does not vanish, then we can proceed as follows. Near x 0 y 0, the equation of the curve g x y equal to 0 can be written in the form y equal to h x. Since g vanishes along the curve, therefore, we can write d dx of g, which is equal to del g del x plus del g del y into dh dx, which is equal to 0 at the point x 0 y 0. And again, since x 0 y 0 gives the constraint optimum value, therefore, we can write d dx of f, which is equal to del f del x plus del f del y into dh dx is equal to 0 at the point x 0 y 0. Now, let us suppose that del g del y is not equal to 0 at the point x 0 y 0. Then we can define a parameter lambda, say del f del y minus lambda del g del y equal to 0 at x 0 y 0. Now, if equation 1 is multiplied by lambda and the result is subtracted from equation 2, then we can obtain del f del x minus lambda into del g del x, which is equal to 0 at x 0 y 0. Thus, we have the equations del f del y minus del g del x equal to 0 and del f del y minus lambda del g del y equal to 0, which holds at x 0 y 0. Now, if we set L as a function of x, y and lambda, which is equal to f x y minus lambda g x y, then equation 3 can be written as del L del x is equal to 0 and del L del y equal to 0, and the original constraint g x y equal to 0 is just del L del lambda equal to 0. In other words, the necessary conditions for an unconstrained optimum of L are also the necessary conditions for constraint optimum of f x y. Hence, the function L defined in equation 4 is called Lagrangian function and lambda is called the Lagrangian multiplier. Now, we consider generalized Lagrangian method. We consider a differentiable function z equal to f x, where x equal to x 1 x 2 up to x n belonging to R n, and whose variables are subject to m constraints, where m is less than or equal to n. g I x is equal to 0, where I equal to 1 to up to m and x is greater than or equal to 0. Then the necessary conditions for maximum or minimum of f x are the set of m plus n equations as given below. Del L del x j equal to del f del x j minus summation I equal to 1 to up to m lambda I del g I del x j is equal to 0, where j varies from 1 to up to n, and del L del lambda j equal to minus g I equal to 0, where I varies from 1 to up to m. Here lambda 1, lambda 2, lambda m are called Lagrangian multipliers. Now, these necessary conditions are also called sufficient conditions for a maximum or minimum of the objective function if the objective function is concave or convex and the constraints are equality. Now, let us take an example. Minimize z equal to f x 1 x 2 equal to 3 e to the power 2 x 1 plus 1 plus 2 e to the power x 2 plus 5 subject to x 1 plus x 2 equal to 7 and x 1 x 2 greater than equal to 0. For this problem, we first construct the Lagrangian function L as L equal to f x 1 x 2 minus lambda into x 1 plus x 2 minus 7, which is equal to 3 e to the power 2 x 1 plus 1 plus 2 e to the power x 2 plus 5 minus lambda into x 1 plus x 2 minus 7, where lambda is the Lagrangian multiplier. Now, the necessary conditions for minimum of f x 1 x 2 are given by del L del x 1 equal to 0, which gives 6 e to the power 2 x 1 plus 1 minus lambda equal to 0, del L del x 2 equal to 0, which gives 2 e to the power x 2 plus 5 minus lambda equal to 0, and del L del lambda equal to 0, which gives minus x 1 plus x 2 minus 7 equal to 0. If we solve these three equations, we get x 1 equal to 1/3 11 minus log 3 and x 2 equal to 7 minus 1/3 11 minus log 3. We will take another example. Find the dimension of a rectangular parallelepiped with the largest volume whose sides are parallel to the coordinate planes to be inscribed in the ellipsoid g x y z is equal to x square by a square plus y square by b square plus z square by c square minus 1 is equal to 0. Let the dimensions of the rectangular parallelepiped be x, y and z. So, its volume which is to be maximized is v x y z equal to x y z. Then the Lagrangian function can be defined as L equal to v x y z minus lambda g x y z, and then the necessary conditions for optimum of L, del L del z equal to 0, which gives x y minus 2 lambda z by c square equal to 0, and also del L del lambda equal to 0, which gives x square by a square plus y square by b square plus z square by c square minus 1 is equal to 0. Now, multiplying the first three equations by x, y and z respectively and adding and making use of the last equation, we can obtain 3v x y z minus 2 lambda equal to 0, and this gives lambda equal to 3 by 2 v x y z, which is equal to 3 by 2 x y z. Thus, we can find x as a by root 3, y as b by root 3 and z as 3 by root 3 as the dimensions of the parallelepiped. We were discussing the Lagrangian method for solving nonlinear programming problem with equality constraints. In this method, sometimes it may be difficult to find solution or to solve the system of equations in xi's and lambda's. So, in that case, a convenient method may be to assume the values of lambda i's successively and then solve the system of equations in xi's. The process can be repeated until the values of lambda i's and xi's satisfies the necessary conditions. Another method may be the dynamic programming method by using Bellman's principle. Let us proceed to find the sufficient conditions for optimum. Case 1. In this case, we consider single equality constraint. Consider the NLPP in which n variables and single constraints are involved. Maximum or minimum z equal to f x, where x belongs to R n, subject to g x equal to 0 and x is greater than equal to 0. The Lagrangian function is defined by L x lambda is equal to f x minus lambda into g x. The necessary conditions for a stationary point to be a maximum or minimum are del L del x j equal to 0, which gives del f del x j minus lambda del g del x j equal to 0 for j equal to 1 to up to n, and del L del lambda equal to 0, which gives minus g x equal to 0. The value of lambda is obtained by lambda equal to del f del x j divided by del g del x j for j equal to 1 to up to n. Now, the sufficient condition for a minimum or maximum need the computation of n minus 1 principal minors of the determinant for each stationary point as given below. The determinant is shown in the slide, and if delta 3 is greater than 0, delta 4 less than 0, delta 5 greater than 0 and so on, that is the minors of order 3, order 4 and order 5 are alternatively positive and negative, then the stationary point is a local minimum. And if delta 3 less than 0, delta 4 less than 0, delta 5 less than 0 and so on, that is the minors of order 3, 4, 5 and so on are always being negative, then the stationary point is a local minimum. We now consider an example. Optimize z equal to 2x1 square plus x2 square plus 3x2 square plus 10x1 plus 8x2 plus 6x3 minus 100, subject to x1 plus x2 plus x3 equal to 20 and x1, x2, x3 are all non-negative. We construct the Lagrangian function L as L equal to 2x1 square plus x2 square plus 3x3 square plus 10x1 plus 8x2 plus 6x3 minus 100 minus lambda into x1 plus x2 plus x3 minus 20. And obviously, the necessary conditions for optimum will be del L del x1 is equal to 0, del L del x2 is equal to 0, del L del x3 equal to 0 and del L del lambda is equal to 0. Solving these 4 simultaneous equations, we get the stationary point x star as x1, x2, x3 is equal to 5, 11 and 4, and also we find lambda is equal to 30. Now, we evaluate the n minus 1, that is 3 minus 1 equal to 2 principal minors at the stationary point x star. So, we evaluate delta 3 and delta 4. Delta 3 gives the value minus 6, whereas delta 4 gives 48. Since delta 3 less than 0 and delta 4 greater than 0, therefore, the extreme point x star is a local maximum. And at this point, the value of the objective function is z star equal to 281. Case 2. In this case, we consider more than one equality constraints. Consider the following NLPP: maximize or minimize z equal to f x where x belongs to Rn, subject to the constraints gix is equal to 0 for I equal to 1 to up to m and x is greater than equal to 0. Then the Lagrangian function is given by L equal to fx minus summation I equal to 1 to up to m lambda I gix, where m is less than n, and lambda 1, lambda 2, lambda m are Lagrangian multipliers. One may verify that del L del xj equal to 0 for j equal to 1 to up to n and del L del lambda I equal to 0 for I equal to 1 to up to m are also the necessary conditions for stationary points of fx. So, the optimization of fx subject to gix equal to 0 is equivalent to the optimization of La. Suppose that the function Lx lambda, fx and gix all possess partial derivatives of first and second order with respect to the distant variables. Let M be the matrix of second order partial derivatives of Lx lambda with respect to the distant variables as shown in this slide, and V be another matrix and m by n matrix for I equal to 1 to up to m and j equal to 1 to up to n as shown in this slide. We define the square matrix HB equal to OV V transpose m, which is an m plus n by m plus n matrix, and the matrix HB is called the border Hessian matrix. The sufficient conditions for maximum and minimum can be stated as given below. Let x star lambda star be the stationary point for the Lagrangian function L and HB star be the value of the corresponding border Hessian matrix. Then x star is a maximum point if starting with principal minor of order 2m plus 1, the last n minus m principal minors of HB star have alternating sign starting with minus 1 whole to the power m plus n sign. X star is a minimum point if starting with principal minor of order 2m plus 1, the last n minus m principal minors of HB star have the sign of minus 1 whole to the power m. The above conditions are only the sufficient conditions for identifying an extreme point, but not the necessary conditions. That is, a stationary point may be an extreme point without satisfying the above conditions. We now consider the following example. Optimize z equal to x1 square plus x2 square plus x3 square subject to x1 plus x2 plus 3x3 equal to 2, 5x1 plus 2x2 plus x3 equal to 5 and x1 x2 greater than equal to 0. The Lagrangian function L is defined as x1 square plus x2 square plus x3 square minus lambda into x1 plus x2 plus 3x3 minus 2 minus 2 into 5x1 plus 2x2 plus x3 minus 5. Then the stationary point x star lambda star can be obtained from the following necessary conditions. Del L del x1 equal to 0, del L del x2 equal to 0, del L del x3 equal to 0, del L del lambda 1 equal to 0 and del L del lambda 2 equal to 0. Solving these equations simultaneously, we get the solution as x star is equal to 37 by 46, 16 by 46 and 13 by 46, whereas lambda star equal to 2 by 23, 7 by 23. From this stationary point x star lambda star, the border Hessian matrix can be obtained as shown in this slide. Here we have m equal to 2, n equal to 3. So, n minus m equal to 1 and 2m plus 1 equal to 5. This means that we only need to check the determinant of h b star, and it must have the positive sign, that is the sign of minus 1 whole to the power 2. Since determinant h b star is equal to 460, which is greater than 0, therefore, the extreme point x star corresponds to the minimum point. In this module, we have discussed the nonlinear programming problem with equality constraints. We have discussed the Lagrange multiplier method for solving this type of problem. We have derived necessary and sufficient conditions for optimum in case there is only one constraint or there may be more than one constraints. We have demonstrated the method by taking some examples. With this, we end this module.